low-cost gas metal arc welding based wire arc additive manufacturing machine. So as we know, 3D printing to build part also called as additive manufacturing or additive layer manufacturing, ALM. So to produce this ALM, we require a computer control process that deposit material in layers to construct three-dimensional object. In traditional, we use to create the 3D project using the machining and subtractive procedures to remove the excess material. But in additive manufacturing, we add layer by layer until we obtain the shape that we want. So this figure here shows how 3D printing using additive layer manufacturing in straight line shape. So before I go far, let me explain what is gas metal arc welding. One of the most prevalent of welding method is gas metal arc welding. So by using gas metal arc welding, an electric arc is generated between the metal and wire electrode during the process, which hits the metal pieces. So to perform the welding process, we need the welding machine, wire feeder, shielding gas, and also welding gun, or also we call as welding torch. Okay, so this is the classification of metal additive manufacturing. So under their direct energy deposition, we have wire arc additive manufacturing, which I will explain more in details. So what is wire arc additive manufacturing? It is a variation of direct energy deposition technology, uses an arc welding process to 3D print metal part. So our team in Metal Forming Lab USM developed a low-cost 3D printing machine for metal using the concept of wire arc additive manufacturing. As we can see here, this is the part produced using wire arc additive manufacturing. And after we milling it, we can see this shape. Okay. I would like to emphasize the problem statement for this project. The first one is metal 3D object, usually created by a large and expensive machine or robot. And the second one is manual 3D printing is not fit for non-professional welder. The ability and experience necessary to manage the 3D printing process. Why we want to build this machine? The team decide to transform the CNC machine into 3D printing machine because we can use for teaching and learning purpose in order to meet the demand of having consistent, mobile, automate, and cost-effective facility to generate 3D profile using metal. That is why we motivate to complete this project. So this is our custom-made metal 3D printing machine that we produce using modular design base, which interface with laptop or PC to develop the toolpath using the G-code programming. So the full machine dimension is 720 times 520 times 1150 mm. So we have CNC machine here and MIG machine below here. This is the total cost to build this machine, including one set of MIG welding machine and the CNC machine, which is XYZ rotor, we call it. And the cost of machine 3D printing in market is very expensive, as we can see here. USD 110 and 400 to 500,000. Okay, let me show you with the real picture of our Metal 3D printing machine. The stage of developing this machine are divided into two stages, where the first stage we identify the parts and their purpose, and we create the CAD modeling of full machine design. And then we start to fabricate the table of the machine. There are three reconfigurable systems in our 3D welding machine. The main part identified is modified CNC machine. This machine is to move the welding torch in X, Y, and Z axis. We also have MIG welding machine. This machine is to produce the welding bed on substrate, which including welding gas, welding torch, and all the accessories here. And we also have the programming software. We use open source GRBL software. This software is to move the machine, which we control by laptop, or we also can use jogger when we install the program inside the jogger. In the second stage, we have the final assembly of the machine body, and testing are conducted to identify the lowest and maximum setting for each parameter that can be adjusted in producing the metal 3D part. For MIG welding, we can adjust the feed rate, voltage, and current, while for CNC, we can modify the speed, delay time, number of layers, and the shape that we want according to the experiment we designed. This is the full schematic diagram for our machine. It's including all module that I mentioned earlier. So we also add some additional features to improve the machine system. So we have a trigger. We modify a switch. We modify a switch at the side of the machine to replace the on and start and stop the welding process. And the second one is the welding torch. We custom the torch holder because the previous one is used for engraving tools for CNC. We also add the linear guide rail at the back of the machine to allow a smooth movement for the welding torch, and it's also helped to absorb the weight of the welding cable, of the torch cable. And we also have the GI plate here to cover the stepper motor from heat. To avoid the welding spark, we add the glass wall of 5 mm thickness at the front and sides of the machine. And the last one, we have the small compartment here to store the glove, G-clamp, eye protector, and other accessories. Okay. We are now in the process of developing a well-maintained machine. So this machine continually being improved from time to time. Until now, some changes were performed, such as raising the height of the CNC machine from this height, and we custom this holder to increase the height of Z axis. We also already include the start and stop printing process in the programming, because previously we used switch at the side of the machine, but now we use start and stop using the program. Next, the torch holder is then improved from this to this one, because when we use this torch holder, it's going to melt during the depositing process because of heat. We also have new jig to retain, this is the old jig, and now we have this jig to retain the substrate from moving during the printing process. Previously, we utilized 100% CO2 gas for my steel wire and 100% argon gas for stainless steel wire. But we need to change the filler wire. We need to change the gas when we change the filler wire. So we use the new improvement here. We can now easily configure the gas what we want. We just flip the valve here. The machine's ability is to deposit the shape that we define from the program. But for now, we just tried three shape. We have the straight line shape and square shape and the circle shape. This all we produce using our machine. But to obtain the actual shape design, we combine both additive and milling process. This is the example of specimen that we use to use the circle shape. This is the actual shape, and then after milling, we got this. So back to what motivates us to produce this machine. As we produce this machine is for learning purpose, I would say there are many people get benefit from this machine. The first one is the third year and fourth year student in mechanical engineering program, because they use this machine for their open-ended lab project. And the second one is the final year student. We already have 3 final year students that use this machine, including the one from School of Material Engineering. The next one is master student, and of course, the last one is researcher, including research officer and the lecturer. Coming soon, we will have a PhD student that are going to use this machine for his project on wire arc additive manufacturing. So far we have used this machine to investigate few subjects, including hardness, strength, defect measurement, efficiency, and tribology. But I won't go into detail about this experiment. I would say that many subjects that can be studied using this low-cost machine. In all this project, we use stainless steel, mild steel, and also aluminium. Just a quick example for open-ended lab project conducted by fourth-year student. They conduct the project on machine's efficiency to observe the waste issue using this machine. Their objective is to calculate the efficiency of metal arc additive manufacturing from the difference in weight of printed part using different parameters. The parameters for their experiment are travel speed, wire feed rate, and distance torch from substrate. At first, they set the machine for wire feed rate and the travel speed, and then they weight the filler wire. Then they run experiment. They weight again the filler wire after experiment, and they repeat the step 3 and 4 using the same parameter for 2 times to get the average. Then they calculate the average for that setting, and the last one they calculate the efficiency of that machine, and they repeat the experiment for the other settings. This table presents the data of their experiments. As you can see here, the highest efficiency of the machine is when using the highest travel speed, which is 150, and lowest wire feed rate, and higher distance from torch to substrate, which is 20 mm. The efficiency of this experiment is 98.839%. So efficiency calculation they get from Benton C in 2021. Okay, my present research is focused on bimetal part. I produce bimetal part using my steel and stainless steel, which is ER208L and ER270S6. This is how we print the my steel and stainless steel. The first layer, and then the torch will move up and go to the first position, and then start printing the second layer. This is the final look of that bimetal part, and this is the longitudinal cross section. This is the example of bimetal gear by Politis 2017 and bimetal bushing by Barron's 2018. Why we want to study about the multi-material? Because of course it's saving costs because we combine the pricey and not so costly material. And the second advantage is lighter in weight. Okay, but this machine it still have its limitation. The first one is limited moving space because the limited moving space is actually only in z-axis because we can't move any further. Sorry. We can't move more in z-axis because we only have 28 mm to move. And the secondly is the part produced is not really consistent, and the tip, contact tip in welding torch is always stuck. So before we want to depositing another layer, we have to clear the contact tip. And then another limitation for this machine is no cooling system yet, but still in our consideration to include the cooling system such as fan, but it depends on the experiment need the cooling system or not. As the conclusion, a low-cost 3D welding machine able to create 3D parts, and the modularity of each module containing welding and CNC rotor allows the reconfiguration of parts and function. And the finding from this project, the machine produced is literally low cost because it's below 3K, and the 3D profile can be used for further metal study. Maybe in future work, we might focus on another improvement and performance of the printed part so that the quality and accuracy of the part produced comparable with the part produced using expensive machine in the market. I think that's all from me. Thank you for listening.
Okay, thank you for Zarirah for her presentation. We will open for Q&A after this, after we complete the second presenter. Okay, without further delay, I would like to call Mr. Faris present part of his master work. Okay, Faris, you can start now.
Okay, so with my this. Okay, first of all, everybody can hear my voice. Uh,
Yes, you can hear
okay.
loud and clear.
Okay, can you see my slide over here? All right. Okay, so
Yeah.
okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon to all of you. So my name is Muhammad Farid Akmal bin Mumazdin, and I'm a master student in School of Mechanical Engineering. So today I want the, to give more detail of my study research, which is the tribological study of additive manufacture, alloy ER5356, based on a pin on this wear test. So we started now. Okay, first of all, I want to actually introduction. I want to talk more detail about aluminum alloys. Okay, aluminum alloys have been widely used in the aerospace and automotive industry for additive manufacturing application. So they are external corrosion resistance, good weathering, and chemical resistance. Figure 1 shows that it's an aluminum alloy application in the automotive component of a typical passenger car, which is grade 5 triple X and 6 triple X series. Okay, so additive manufacturing. What is additive manufacturing is? It's the industrial production name for 3D printing. It's a computer control process that creates three-dimensional object which by depositing materials, usually in layers. As shown in figure 2, an example of 3D printing of additive manufacturing. So, okay, additive manufacturing is or AM, is an alternative to typical practice for part damage. I mean, for example, instead you send to landfills, we are AM is offer quick and flexible part modification through remanufacturing and repair. Today, AM is still used to make metal components from metals, which is titanium, nickel, and aluminum, commonly used in a lot of application in automobile industries. Okay, the most suitable additive manufacture process for larger components, which is the direct metal deposition DMD, which called wire and additive manufacturing WAM. Figure 3 that shows an example equipment of WAM. Okay, this is a schematic diagram of the setup of wire arc additive manufacturing, which is the WAM. You see, the WAM, right, is executed by depositing layers by layers of metal on top of each other until a desired 3D shape is created with the voltage, current, travel speed, argon gas, and feed rate already set up. So this is the figure 5. It shows the current apply of uses of additive manufacturing in automotive industries. As you can see, the current that by AM is exterior trim, which is the bumper windbreakers, which the material is polymer. The fluid handling pump, for example, pump and valve, which is use the material aluminum alloys. The manufacturing process, for example, prototyping, customized tooling, they're using polymers, wax, hot wheel steels. And lastly, exhaust slash emission, which is the application is a cooling van, uses the aluminum alloys. This is the current apply used for AM in automotive industries. However, friction and wear have become the primary cause of part failure due to the severe wear, particularly for for the parts that including the sliding mechanisms. This also limit the use of material with low wear resistance, which such as aluminum alloy, which offer excellent weight reduction. In addition, there are other factors such as loads, test duration, temperature, humidity, which affect wear mechanism and wear resistance. Wear is a complicated phenomenon that influenced by a variety of factors, which is microstructure, manufacturing method, sliding material, thermal characteristic, and lastly, the mechanical qualities. Okay, porosity also is one of the main problem of in WAM of aluminum alloy, which can severely limit the mechanical properties of the part. Porosity is generated as a result of the several factors, including the arc welding process parameter, interpass temperature, wire quality, and alloy composition. So therefore, when part require a post-process treatment to improve the material property and porosity, by appropriate application of post-processing, the majority of issues that relate to the properties, including the wear of the material, can be addressed. So, there are few post-processing techniques for the purpose of the material property improvement. Number one is the post-processing heat treatment. Second, interpass cold rolling, pinning and ultrasonic impact treatment (UIT), and lastly, rapid cooling. Post-process heat treatment. What is post-process heat treatment? It's where the sample was heated in the muffled furnace and quenched in the cold water during the solution treatment procedure. This, this process will reduce the residual stress, enhance material strength as a method of a hardness control. There are researchers have argued that a higher interface temperature is even desired when producing an alloy component as it leads to reduced porosity. Second is the interpass cold rolling. It's a process which a metal is passed through roller at a temperature below its recrystallization temperatures. So the metal is compressed and squeezed, increasing the yield strength and hardness of the metals. We also lower the residual stress and increase material property, as well as improving the microstructural properties, which reducing the porosity and improvement of the mechanical properties. As shown as a figure 8 over here, is the interpass rolling in vertical on the left side, and the right side is the side rolling. So now it's a more detail about pinning and ultrasonic impact treatments. It's a cold working process that uses a high frequency and high velocity impact onto a workpiece, this one is the workpiece over here, of the specimens. As shown as figure 9, is a schematic diagram of the surface microstructure fabrication by using ultrasonic impact treatments. The researcher stated that this treatment will reduce local residual stress and improve weld mechanical properties. Lastly is the rapid cooling process. Okay, the cooling spray was initiated after deposition of each layer was completed in order to avoid arc disruption caused by the relatively turbulent carbon dioxide flow. They has shown that have the better surface finish and increased tensile strength at lower interpass temperature, 100 degree or less. There is another process method in order to enhance material property, which is forging. Forging is a manufacturing method that involves shaping metal using high concentrated compressive stresses by hammering, pressing, rolling. So you can produce high quality, robust product under temperature control circumstances. There is hot, warm, or cold forging according on the temperature at which the forging process is carried out. So objective of this study is to study effect of the tribological parameter of the wear rates and to investigate the effect of the cold forging to the tribological and mechanical properties. So this is my overview for my studies. First of all, okay, in this study, the WEM I was utilized to produce 3D profile from an aluminum alloy grade ER5356. So the wear test conducted according to ASTM G99. Beyond this for both dry and wet sliding conditions. So order to start here, in order to get the 3D welding specimen test, we must input the parameter data, which is the voltage, traverse rate, and feed rate. Now, after we put several input parameter data, if the quality of the specimen, which is the good bit size, you can use the value data to produce more specimen. If you're not, the data will not selected and disposed. And after we use that from data to create a 3D welding specimens, 3D welding specimens, the specimen was separated into both cases, to unforged and forged cases. So to make a forged specimen, the welding bits specimen will go through the cold forging mechanical press, and the unforged specimen will go straight away to milling machining. So why reason why I use cold forging? Because cold forging is widely used for an experiment because it's easy to use and low cost. There are several studies about cold forging state that the yield strength, tensile, and hardness increases while toughness. When the yield strength and tensile and hardness are increases. After they already forged by mechanical process and milling machining, both cases are straight to surface finishing late in order to get the fabrication specification. Now, right up all the specimen for both cases will check for quality. If they had both of them have no defect cresti, it will proceed to do pin on this test. If not, it will dispose the failure specimens. For the for both cases, we'll proceed to do on pin on this wear test. For both sliding tests, which is wet and dry sliding test. Right after that, for both unforged and unforged, we proceed to Alicona wear image for wear observation. Reason why I use Alicona wear image instead of SEM. The reason is to obtain the micrograph wear image size. Right after I get wear image results, I will the both for both specimen will proceed to do hardness test with using rod wells. That's all for my overview experiment for my studies. So this is a schematic diagram of WAM MIG base for my studies. All the samples were prepared using in-house WAM printing equipment, which MIG 3D welding. The nozzle position, this is the nozzle position, was determined from CNC command software derived for the personal laptop, which you're using the personal laptop. Rendition of the desired part. Sorry, the part while using open source software configurable control Candle version 1.17, which detect the motion command to the microcontroller. Then the deposited material metal was printed directly onto the MySteel base. Right. This is the welding parameter that's set up for the studies. The table below is the material property of aluminum ER5356. Okay, for your information, MFRL 5356 is a magnesium base in the grade of 5XXX series. Oh, so this my figure 11 is shown a single bit deposition of element alloy ER5356 of my specimen is. Okay, for forged cases, right, the specimen will proceed cold forging process, which is a mechanical press as shown in figure 12. So the thickness of the specimen should be forged until it reach 10 millimeter, and we'll get the forged specimen as shown in figure 13, like for the end here. After that, the specimen for both cases will proceed through the milling process and followed by turning process to achieve intended dimension. 6 millimeter diameter cylindrical pin is shaped as indicated by ASTM G99 standard as shown as a figure 13, which is specimen specification. And figure 14 is the fabricated specification. And then the die penetration will be applied to check for defects such as crack and erosion. So this is an illustration of the test procedure of the pin on this test as shown in figure on this figure. Okay, so the test is following ASTM G99. The pin on this setup are depicting a pin on this tribometer. Okay, the test will begun on the bottom specimen with the reciprocating speed start off by 200 RPM, and then the procedure repeats on other specimens with different parameter as for both and wet and dry as sliding as listed as shown below this table. So to compute the time required for each die, use the volume formula in equation 1. Okay, so for wet sliding, right, the lubricant used for in this experiment is fully synthetic oil, FW40 Akaya. The lubricant was applied on top of the surface of the rotating disc the lubrication between the rotating disc and stationary pin. The lubricant was applied. So that it can creating the lubrication between the rotating disc and stationary pin. Now we straight to the results. Okay, the results. This is the result for dry sliding in speed versus average of specific wear rate for forged and unforged cases. Now, as you can see from here, right? Look at the pattern. This is the pattern for my result. As speed and load increases, for both cases, the average specific of wear rate also is decreases as speed and load increases from 200 rpm to 400 rpm for different loads from 10 newton to 30 newtons for both cases. But if you compare forged and unforged, forged specimen are have the lower wear rate, lower average of specific wear rate than the unforged. This is the result for wet sliding in speed versus average of specific wear rate for forged and unforged cases. As you can see over here, the trend are from going from low to high. It means that as speed and load increases, the average of specific wear rate for both cases in wet sliding are also increases. The If you compare for both cases, forged also low of average of specific wear rate than the unforged. Okay, so this is the result for hardness in unforged cases with different speed and load. Now, they are these hardness value are vary from 200 pm from 63.4 and the highest is 64.2. For 300 rpm, the lowest is 63.0 but the highest is 64.9. Meanwhile, for the 400 rpm, the lowest is 61.6, while the highest is 63.8. It shows that for this unforged, as speed and load increases, the lower the hardness is. Now, the result for forged cases in hardness value is, it shows that the value for 200 pm for each load, the lowest is 63.3 for 20 Newton wet and 20 Newton wet. The highest is 67.5. For 300 pm is the lowest is 64.9 and the highest is 67.6. But for 100 rpm, the lowest is 64, but the highest is almost similar, which is 69 or 69.1 for 10 Newton dry and wet. But if you compare forged and unforged, forged has the hardness for forged is higher than the unforged. So we straight to the conclusions. Okay, WEM offer quick and flexible part modification of manufacturing and repair. Okay, so for both forged and unforged cases of aluminum alloy ER5356, the specific wear rate decreases as speed and load increases for dry sliding. This is because the heat generated from the sliding surface between aluminum alloy ER5356, forged and unforged, and this has softened the aluminum alloy and reduces its hardness, which resulting in low specific wear rate. Meanwhile, for the wet sliding, the average specific of wear increases as speed increases, which indicates the changes of lubrication regime during sliding. So this is my recommended future works. So the future work, the following are recommended. One is to conduct experiment for sliding distance higher than 1,000 meter to assess the wear rates. And second of all, to investigate the rheological effect of cold forging in optimizing the manufacturing process of the automotive component parts, which lead to the improvement of the rheological performance of the deposited material via arc additive manufacturing. So, acknowledgement, I want to like to acknowledge USM for sponsoring this project under SATU Joint Research Scheme for U2021. And I also like to thank you, my supervisor, Associate Professor IR Dr. Ahmad Bahrudin bin Abdullah, for his guidance throughout this research. This is all the reference already stated in the slide. So that's all for me. Thank you so much for listening. That's all.
Okay, Thank you, Faris, for the presentation.
Okay, thank you again.
I would like to open for any question from the audience. You just name to who you want to ask and what is your question. Okay, before we get some question from you, I think I just want to highlight about the satu joint scheme grant that been mentioned by Faris just now. Okay, satu is Southeast and South Asia and Taiwan University Cooperation is a platform where created by the one of the top university in the Taiwan, so that any members under the satu can collaborate between them in any projects. However, they are not the organizer will not give any fund for the research. Only the host university will provide the grant. Is we call as a matching grant, and it's good if in terms of international collaboration, especially for this project. We collaborate with UTM on the Shahid, and as well as Prof. Rajendran from SRM Institute of Technology India. This is a 2 years project and funded by University Science Malaysia as the under the matching grant as the host university. Okay, we received a first question from Dr. Shahid. He asked Puan Zarirah, how do you manage the generation or execution of G code for the machine? Yes, Puan Zarirah.
Okay. Like this. We generate the solid for the circle shape. For the straight shape, we just generate the G code. We just line the G code in the programming using the RBL software. But for the circle shape, we use the Autodesk software to generate the shape first, and then we generate the G code from there. And to make the additive printing, we manually increase the layer by layer by increasing 1 cm from the previous layer before printing the second layer. Can you understand me, Doctor?
Boleh, Wan.
Okay.
Okay, actually, the CNC router is it also have its own software. It's a open source software where we can generate the code from that for simple programming, or probably a straight line. Probably if you want to more complex, probably we requires any CAD and CAM software to do or to create the G code. All right. Next question by Dr. Noazam from the NTI. To Puan Zarirah, do the gas that cover the welding work affect the welding process in terms of gas flow?
Yes, it's affect the welding process. But for now, we use 10 liter per minute. I think 10 liter per minute for every experiment that we have done, because I know there's a research that use gas flow rate as their parameter also, but for our team, for our research done, we only use 10 liter per minute. Maybe in future we can try some parameter on gas flow rate also. That's affect the welding process and the welding bit.
Okay, next question from Zul Khairi Rizlan. To Zarirah as well.
Okay.
For the sample produced by the machine, what are the tests that have been done? Maybe in terms of strength or defects, for example.
Okay. To measure the strength, the students have done the viscous hardness test and rock weld test. And for strength, we also have a Chappie impact test, nano indentation, and for defect test, we already use salt spray test and dye penetration test.
Yeah, next question to Zarirah as well, from Anna Rosli. How you control the wire feeding system to align with the G code?
Control the wire feeding system to align with G code. We just control the wire feeding at the machines because there's already knob on the machine that we can control um, what per minutes we want to the wire feed. In the G code we just specify the travel speed and number of layers only.
So means that we can control the feed rate lah.
Yeah, we can control the feed rate.
Wire feed rate.
We can control the wire feed rate on the machine, not in the software.
Okay, how you integrate that? How to integrate between the software, the G code, which is the G code, as well as the machine. Do we need to key in the value of feed rate into the G code, or?
No, we don't have to. Because we just control it on the machine.
Okay, hopefully it's answer the question from Anna Nosli. Okay, next question to Mr. Faris. How does the tribological properties of WAAM forging sample in your study compare with that of conventional produce sample? Faris, unmute.
Sorry. Okay. So how to compare my tribological property of my produce samples with the commercial produce sample? I may compare with mechanical properties. I suppose in hardness, it shows that on my samples, my hardness are more higher to compare with the conventional. For example, milling, milling and yes. If you yeah, I think I think because if you compare hardness between, for example, I using forged samples, my hardness value is increased. For example, conventional, for example, milling already my lowest hardness is 64, while the forged samples is vary from 65 to 69.1. I think that's maybe I answered the questions.
Okay, next question is from Azam as well. I think it's for Puan Zarirah. How you control time delay between one layer to another? Is it can be controlled in GBRL program?
For now, we do it it's semi-automatic lah. It's not so fully automatic because we just produce the first layer only. For the second layer, third layer, and fourth, and so on, we just use a manual, what you call, manual. We do it manually because uh, in when we use Autodesk Fusion, it's used for um, CNC machining, and that is what we call it's terbalik daripada apa yang kita buat untuk additive. Untuk buat using Autodesk tu, kita macam subtractive punya part machining. Kita machine dia. Kita machine from the square shape ke. Tapi untuk yang ni kita nak additive. Kita nak create layer by layer. So untuk kita nak buat dia automate control delay time, tak dapat lagi setakat ni lah untuk using this low cost machine. Mungkin in future kalau kita study lagi, mungkin boleh dapat. So untuk software GRBL tu pun, I'm not really expert lagi lah on that. Still in learning process because we just start this using this machine 2.5 years ago, I think. Hopefully, if any of you have using the CNC machine also, can share what's your project. Boleh Dr. Azam?
Alright,
Okay, okay.
thank you.
Thank you. Sebab apa? Saya nak tanya, bila kita buat layer by layer tu, contohnya
Yeah.
kita bergerak dari point A ke point B kan?
Ya,
Then dari situ kita akan buat layer kedua di atas on top of it kan?
betul.
So sekarang ni bila kita stop di situ, kalau pakai GBRL, dia sama macam CNC, dia boleh juga kita programkan dia. Cuma problemnya ialah bila kita stop di satu point tu, dia punya torch still menyala lagi kan? Still
Torch
menyala.
tak menyala because we stop.
Oh,
Kita stop and then rise
Sampai
up
berapa
and then
saat
go
minit
to
tu
the
kita
first
round
position,
untuk yang layer
baru
kedua
run
kan?
balik. Ya.
Okey. Maksudnya sekarang ni manual dia kita buat, bukannya kita pakai program lah.
Pakai program on the first layer, untuk next layer pun kita pakai program.
Faham.
Macam ni,
Maksudnya
macam
sampai
ni.
ke point B tu kita stop.
Kita stop dekat point B and
Manually
then
kita
kita
stop kan,
naik
kita tak pakai
atas.
program kan. Okay.
Stop pakai program, lepas tu naik atas pun pakai program, go to first position pun pakai program.
Okay, faham. Okay, tak apa. Terima kasih. Okay, thank you.
Okay.
Yeah, thank you for the question. Actually, as I think Dr. Zarirah already mentioned, this is a semi-auto machines. These some of the tasks need what we call as manual touch before we can proceed with the operation that we want to conduct based on the programming that we have set. Actually, we still learning about that. We still exploring about the machines. To buy probably take some time. Probably those who are being some time with this YR additive manufacturing, probably from UTEP, probably they already faced this before. We try to explore and try to get the best what we call as profile as possible using this machine in the future. Is there any other question? You can type or we can ask it verbally. Yeah, laser engraving, yeah.
Okay, Dr. Azam. Later we collaborate.
Okay. If no question, allow me to as I mentioned before, we are planning for another series of webinar. Hopefully, by end of this year. Sorry. Yeah. Okay. We plan another webinar at the end of probably tentatively at the end of the November 2022. Hopefully, we can do that. We have two PhD students. One Muhammad Fadil Jamaluddin from UM. He's now with UM. And Mr. Muhammad Zulhairi. Sorry. Both are doing project on aluminum to steel teller welded blank. One, Mr. Fadil will you are using the laser welding, whereas Mr. Muhammad Zuhairi used the friction stir welding. Hopefully, we can realize that. Hopefully, we can get more audience because this is the first time. I think there are many things we can improve, especially when we talk about online. Sometimes we can control sometimes it's out of our control. Okay, before we end the session, can I? Okay, for the e-certificate, if anybody want to have the certificate but did not register before, please type your full name in the chat box as well as your email so that we can prepare the certificate and send to you as soon as possible. The list for those who are already registered, we do have, and we'll send to them as soon as possible. All right. Before we end, can I get can we have a photo session, please, so that please switch on your camera so that we can see your face and then okay. I will screenshot. Okay, 1, 2, 3. Okay, freestyle. As usual, it's a common. All right, 1, 2, 3. Okay. With that, I think that's the end of the webinar for today. Hopefully you get something. If you have any question to ask further after this, please do ask and can send email to me or you can directly ask for Zarirah or Faris for that particular project. Okay, with that, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Hello,